Good morning to all. This is Dr. A. Sarnath Babu, Assistant Professor of Physics, Annamacharya Institute of Technology and Sciences, Rajampet. Today I discuss the types of polarizations. So already you know the definition of polarization. Polarization is the separation of positive charge centers and negative charge centers on the application of electric field. Here polarization occurs due to several atomic mechanisms. When a specimen is placed in DC electric field, four types of polarizations occur in dielectric material. First one, electronic polarization. Second one, ionic polarization. Third one, dipolar or orientational polarization. Fourth one, space charge polarization. So first we discuss the electronic polarization. Displacement of nucleus and electron cloud in opposite direction to applied electric field is called electronic polarization. When electric field is applied on dielectric atom, electron cloud is displaced with respect to the nucleus in a direction opposite to the electric field. This phenomenon is called electronic polarization. So here let us consider one atom without electric field, no electric field, E is equal to 0. Then in the atom there is nucleus. Inside the nucleus, positive charged protons are available. Next, around the nucleus, electrons are revolving in particular orbits. Here, if there is no electric field, the positive charged nucleus center is coincided with the electron cloud center or orbit center. So there is no dipole, there is no polarization. So next, here consider an atom of dielectric material such that its atomic number is Z and atomic radius is capital R. The centers of electron cloud and positive charge nucleus are coincided. Hence, there is no dipole moment. Here, let us calculate the negative charge density of the atom. Rho is equal to, charge density is denoted by rho. Rho is equal to minus ZA. Z is the electron number. E is the electron charge. Electron has negative charge, so we put negative sign divided by volume of the atom. Atom is in spherical shape, so we write the volume of the sphere formula, that is 4 by 3 pi r cube. So when this atom is placed in electric field of strength A due to the Lorentz force, the electron cloud will move in opposite direction. So here, if we keep the atom in electric field, due to the application of Lorentz force, electron cloud move in opposite direction to electric field. Then immediately the Coulomb force will act between positive charge center and negative charge center. So because due to the opposite charge of electron and protons, there is attractive force, that is called Coulomb force. So the Lorentz force separating positive charges and negative charges, Coulomb force attracting positive charges and negative charges. So at equilibrium position, both Coulomb force and Lorentz force both are equal together. Then the separation will be stopped at that distance. So hence dipole moment will be greater than 0. The atom gets polarized. Let the distance between centers of nucleus and electron cloud is x. So here we consider electron cloud center and positive charge center. The distance between these two is taken as x. By taking x as radius, you can draw the imaginary sphere. Total negative charge in the sphere of radius x is QE is equal to 4 by 3 pi x cube into rho. Rho is the negative charge density. QE negative charge, QE is equal to 4 by 3 pi x cube into negative charge density is taken from first equation, that is minus ZE by 4 by 3 pi r cube. So total negative charge QE is equal to minus ZE x cube by r cube, where in above equation 4 by 3 pi gets cancelled, then we get minus ZE x cube by capital R cube. The total positive charge of the atom QP is equal to plus ZE, where Z is the number of protons, E is the proton charge. Proton has positive charge, so we put plus sign. The Coulomb force FC is equal to 1 by 4 pi epsilon naught QE into QP by x square. x is the distance between positive charge center and negative charge center. Substitute in equation 3 and 4 in equation 5. Then Fc is equal to 1 by 4 pi epsilon naught x square into minus Ze x cube by r cube into Ze. Next, Fc is equal to minus Z into Z, Z square, E into E square. In next, x square cube gets cancelled. Then you get x divided by 4 pi epsilon naught into r cube. Next, Lorentz force. Fl is equal to minus Ze into capital E, where on the application of electric field, electron cloud has less mass. So comparatively, electron cloud is displacing in opposite direction to electric field. So we take the Lorentz force. In calculation of Lorentz force, we are taking the negative charge, total negative charge, that is minus Ze into applied electric field. At equilibrium, Lorentz force, Coulomb force both are equal together. Then we are equating these above equations, Fc and Fl. Then we get minus Ze into E is equal to minus Z square E square x by 4 pi epsilon naught into r cube. Next, by taking calculation, Z gets cancelled, E gets cancelled, then we get capital E is equal to minus Ze x by 4 pi epsilon naught into r cube. Small x is equal to 4 pi epsilon naught r cube capital E by Ze. It is equation number 8. Next, induced electronic dipole moment mu E is equal to total charge Ze into x, where we are taking positive charge minus plus Ze into x. Substitute equation 8 in equation 9. Then electronic dipole moment mu E is equal to Ze into 4 pi epsilon naught into r cube into capital E by Ze. Mu E, electronic dipole moment mu E is equal to 4 pi epsilon naught r cube into capital E, where in above equation Ze gets cancelled, then you get equation 10, that is electronic dipole moment mu E is equal to 4 pi epsilon naught r cube into capital E. So from definition we can write that electronic dipole moment mu E is equal to alpha E into capital E. Alpha E is the electronic polarizability, capital E is the applied electric field. So from equation 10 and 11 we can write that electronic polarizability alpha E is equal to 4 pi epsilon naught into r cube. That is equation number 12. The induced electronic dipole moment per unit volume is called electronic polarization. So we can write electronic polarization E P is equal to capital N alpha E into capital A. Next, from the definition, fundamental definitions, we can write the equation of polarization vector capital P is equal to epsilon naught E into epsilon r minus 1, that is equal to N alpha E into E. So electronic polarizability alpha E is equal to epsilon naught into E into epsilon r minus 1 by capital N. That is equation number 13. Next, we discuss the ionic polarization. So some other type of materials, some ionic materials, for example sodium chloride, so that is ionic material, dielectric material. The ionic polarization is due to displacement of cations and anions in opposite directions. So here, if you take the ionic dielectric material, if there is no electric field, E is 0, there is no electric field, cations or positive ions and negative ions or anions that are equally or symmetrically distributed. So positive charge center and negative charge center both are coincided, then there is no polarization, there is no dipoles, so dipole moment becomes equal to 0. When an electric field is applied in positive x direction, then what happens? The positive ions move to the right by x1 distance and negative ions move to left by x2 distance. So by applying the electric field, Lorentz force acting on the ions, positive ions and negative ions. So due to the application of this Lorentz force, the positive ions are moved or displaced by x1 distance. Next, negative ions are displaced or moved by x2 distance. So like this, chlorine is the negative ion, sodium is the positive ion. So sodium is displaced by x1 distance, chlorine is displaced by x2 distance. The resultant dipole moment per unit cell, mu I, ionic dipole moment, mu I is equal to ion charge E into x1 plus x2. Total displacement of positive ion and negative ion x1 plus x2. That is equation 1. If K1 and K2 are restoring force constants of cation and anion, F is the force due to applied electric field. Capital F is equal to K1 x1. So here, if we apply the electric field, the Lorentz force acting on the ions, due to the applying of that electric force or Lorentz force, ions are displacing. So while that ions are displacing, another force, restoring force, will develop in opposite direction. That restoring force is considered as capital F is equal to K1 into x1. Next, restoring force developed on electrons, that is, are negative ions, that is same, F is equal to K2 x2. Then x1 is equal to F by K1, x2 is equal to F by K2, where K1 is the force constant of positive ion, K2 is the force constant of negative ion, where K1 is equal to small m omega naught square. Small m is the mass of the positive ion, omega naught is the angular frequency with which the positive ion is displacing. Next, restoring force of negative ion, K2 is equal to capital M into omega naught square. Capital M is the mass of the negative ion, omega naught is the angular frequency with which negative ion is displacing. So both angular frequencies are equal for positive ion and negative ion. Next, the Lorentz force, capital F, is equal to charge of the ion, small e, into applied electric field, capital E. So at equilibrium position, the Lorentz force and the restoring force, F values, F, both are equal together. Then we can write that small m is the mass of positive ion, capital M is mass of negative ion. Okay. So x1 is equal to F by m omega naught square. F is equal to small e into capital E. Next, x2, displacement of the negative ion, is equal to F by capital M into omega naught square, where F is equal to small e into capital E. Then total displacement, x1 plus x2 is equal to small e into capital E by omega naught square into 1 by capital M plus 1 by small m. Ionic dipole moment, mu I is equal to ion charge, small e, into total displacement of positive ion and negative ion, x1 plus x2. The ionic dipole moment mu I is equal to the small e into e square into capital E by omega naught square into 1 by capital M plus 1 by small m. That is equation number 3. Ionic polarizability, alpha I is equal to mu I by capital E, where mu I is the ionic dipole moment by E is the applied electric field. So ionic polarizability, alpha I is equal to E square by omega naught square into 1 by capital M plus 1 by small m, where the capital E gets cancelled. Then we get ionic polarizability, alpha I is equal to E square by omega naught square into 1 by capital M plus 1 by small m. That is equation number 5. Next, dipolar or orientational polarization. When electric field is applied on polar dielectric material, all dipoles are aligned in the direction of applied electric field. The polarization produced in polar dielectric material due to application of electric field is called orientational polarization. So here you can observe that in the first diagram. So certain molecules have permanent dipole moments. Such molecules are called polar molecules, and corresponding dielectric is called polar dielectric. So in the absence of electric field, all dipoles are in the polar dielectric are random orientation. Then net dipole moment becomes 0. So here in the first diagram, if there is no applied electric field, then these dipoles are randomly oriented. One is in upward direction, one is in left side direction, one is in right side direction, so one is downward direction. So in first diagram, the all dipoles having dipole moments in different directions. So net dipole moment, one dipole moment is cancelled with the other, so net dipole moment becomes equal to 0. Next, when electric field is applied, the dipoles are rotated about their axis of symmetry and aligned in the direction of electric field. The dipole alignment is counteracted by thermal agitation. So in next second diagram, if we apply the electric field, positive charge, if we keep the dielectric material between positive charge and negative charge capacitor plates. Then, by applying the electric field, these dipoles are rotated